Okay, so welcome to today's Journal Club, everybody. It's my very great pleasure to introduce our external speaker, Shivani Bhandari from CSIRO, who has agreed to come and speak to us about her recent papers and the recent work from the ASCAP team about the ASCAP FRBs and host galaxies. So Shivani, it's all yours.
Thanks. Can you see my screen?
Yes.
Okay. Yeah, so good afternoon, everyone. And thanks, Emily and Cherry, for inviting me in the Journal Club today. I would like to present my recent work on FRB host galaxy population today. So this work was done in close collaboration with the RealFast team and Craft team and F4 team. So the paper describing the results has been submitted to AppJ and this is up on arXiv at the moment. Yeah, so just to give a brief outline, so I'll start off by introducing 3 new FRB localization that is included in this work. Plus, I will also talk about some of the previous published FRBs and their host galaxies. Then with these new observations and including the published data from the literature, then I will compare the whole larger FRB host galaxy sample with the underlying field galaxy population. And following that, I will present a differential analysis of the host galaxies of the 2 apparent FRB source populations. So host galaxies of repeating FRBs versus non-repeating FRBs. And then I'll compare the global properties of the FRB host with that of extragalactic transients, and also compare the FRB offset distributions with the galactic sources, and also with the globular clusters in the late type and early type galaxies. And finally, I'll present my conclusions. Yeah, so feel free to interrupt me on any slide if you want to discuss about that particular plot or particular topic in more detail. Yeah, so let's dive in. As we have heard now, FRB 180301, this was originally a Parkes discovery, discovered in the Breakthrough Listen project. And later, when Ray et al. Followed it up with the FAST telescope, they observed repeating bursts from this particular source. So they found 15 repeating bursts, and that's how the source was turned out to be a repeater. So to localize this burst, we conducted follow-up campaign with the VLA RealFast system in L-band and were successful in catching the source during action. So a repeating burst from this particular FRB source was detected with a signal to noise of about 20 in the RealFast 10 millisecond image here at a DM of about 536. Of which Milky Way ISM contribution is about 152, and DM cosmic, which basically is the DM contribution estimated from the McQuart relation for the foreground halos and IgM, and that turned out to be about 290. So as you can see in this picture, the burst is localized to this host galaxy and with a precision of less than an arc seconds here. It is observed to originate from the outskirts of this host, which is basically at a redshift of 0.33. So the plot here is the Gemini R-band image. As far as the association is concerned, it's pretty secure because we computed the path posterior probability, and it turned out to be 99.9%. So we are very confident about the association. If you want very specific or nitty-gritty details about the localization and astrometry itself, please ask me later. But in this talk, I'll mostly concentrate about the host galaxies and the properties of the host galaxies. Yeah, so moving on, the next burst that we detected in Craft survey. So this was in Craft survey, yeah, to mention that. So it is FRB 191228, and it was detected at a DM of about 298, so about 300 at 1.2 gigahertz. So offline interferometric analysis led to the localization of this burst, and we found that the FRB sightline was accompanying this lonely star Fomalhaut in this picture, as you can see. So yeah, so thanks to our heroic efforts from our craft collaborators, we were able to get rid of most of the glare of the Fomalhaut stars. And we saw the host for the very first time in the very large telescope Forest 2 images here. Again, we computed the path posterior probability, and it's 100%. So we are again pretty confident about the association. And again, FRB was seen to come from the outskirts of this host galaxy. The spectroscopy from the Keck telescope confirmed the redshift of the host to be 0.24. And the galaxy has a stellar mass of about 5.5 times 10 to the power 9 solar masses. And the star formation rate is only 0.03 solar masses per year. So not many stars are being born in this galaxy as compared to our own Milky Way. So another detection was from craft survey again, was FRB 200906, detected with ASCAP at a signal to noise of about 19 at a DM of 259. Now for this source, the estimated DM cosmic is 324. So you can see that there is a bit of excess DM from the host this time for this particular case. So we localized the burst to a host galaxy at a redshift of 0.368 with an accuracy of about half an arc second. So it's better than previous detections, which was less than an arc second. So yeah, so we saw the host galaxy when we were going through the archival data on this field, and it was identified in the pan stars. And then we went on and observed the host galaxy with the VLT Forest 2 instrument. So luckily there are no stars in the way to mess things up this time. So this was pretty much straightforward reduction. So we found that the galaxy is an order of magnitude massive than the previous ones we have seen, and star formation rate is about half solar masses per year. Yeah, so next I'll talk about some of the FRBs that are published in literature. So detection of an FRB in the commensal ASCAP craft observation facilitated a search for radio afterglows before and after the FRB event. So FRB 191001 was the very first event that we detected in such a observational mode, when the ASCAP hardware correlator was running and recording visibilities parallel to the craft system. So you can see the FRBs were so bright that it is even detected as an image plane transient in a single 10-second snapshot from ASCAP hardware correlated data. So, and this is the light curve for the whole 9-hour duration. And you can see that we can clearly see in this 10-second snapshot, we can see the FRB here. So we search for any radio emission at the pixel of the FRB before and after the event. So there is like about 8 hours before and maybe 1 hour or half an hour after the FRB event. And we did not find any varying emission above the 5 sigma line. So we only found this FRB here. And then we conducted the follow-up observation for this particular source with the Australian Telescope Compact Array, ATCA, and so the red contours here are the radio contours detected at ATCA for this particular host galaxy here. So FRB is coming from this really tiny portion in the outskirts of the galaxy again. And these contours are 5.5 gigahertz radio emission. So you see that there is no persistent source at this level, but this radio emission is due to the ongoing star formation in the galaxy. So I should mention that the star formation rate for this galaxy was about 8 solar masses per year. So it's pretty star forming. And then you can see that there is a second host galaxy, which is about the same redshift. So pretty much they might be interacting as well. Yeah, so very recently, again, guys reported active nature of a repeating burst, and people started following it all over the world. We also conducted follow-up observations with ASCAP and found repeating FRBs from this source. And we were able to successfully localize the burst to a galaxy at a redshift of about 0.09. So yeah, so we found the host galaxy to be typical star forming. It was very massive than the previous repeating FRB hosts, and it was very dusty. And excitingly, this was dominated by the old stellar population with the mass weighted weight of 5 to 6 gigayears. So Wenfei and et al., they conducted proper prospector stellar population modeling for this galaxy. And that's how they find that it's dominated by older stellar population. So the old stellar population for this particular host suggests that the host can accommodate progenitors that have longer delay times. So we also found the star formation rate of the galaxy to be pretty much constant over 10 gigayears of history, with a notable absence of any starbursts. So which kind of rules out the scenarios of ultra-prompt channels for creating a magnetar, such as superluminous supernova or long GRBs. So those sort of scenarios were ruled out for this particular case. Also, the host properties for this galaxy are pretty much consistent with that of, yes, Mohit?
Can I ask a question? So you said that I can ask when you're talking.
Yeah, sure.
Sure. So regarding the last point, the point that you just stated,
Okay.
I'm not sure if you can actually rule out, is it the case that all these superluminous supernovae or GRBs, they are formed when there is a star formation peak in the star formation history, means there is a star burst activity?
Yes. And also the case that this is not a dwarf galaxy, it's one of the probably most massive galaxy that is ever being found for a repeating FRB. So that kind of, so just looking at the host galaxy property as a whole, we can say that it might not be a place where superluminous supernovas or LGRBs might happen.
That's right.
So
I'm sorry.
Yeah, so I would maybe say that are unlikely rather than completely ruled out. Yeah.
I see. Yeah, I'm thinking about superluminous supernovae type 2. I know type 1 because they are exclusive in dwarf galaxies, but I'm thinking about type 2.
Sure. Okay, yeah, so yeah, as I will mention later, that we really need to chase this host galaxy with Hubble's telescope and really look at the local environment to see like what exactly going on around the vicinity of the FRB itself. Yeah.
I see. Thanks.
Okay. Yeah, so that was that point. But the host properties are consistent with that of core collapse supernovae. So because it's a star-forming galaxy and the masses are in the right range, so the magnetars formed by prompt channels could therefore accommodate FRB progenitors for this particular scenario as well. Yeah, so finally, we found no evidence of a dominant AGN associating the persistent source. Therefore, we think that this this background image, which is the VLA PRS and the GMRT persistent source, which they claim is basically because the radio emission is basically because of the star formation in the galaxy. But yeah, as I said, a high resolution view of the local FRB environment is very important, and that will provide us more clues about what's going on in this galaxy. But this was a really interesting source to study. Okay, so far we have looked at the properties of the individual FRB host, and now we will consider the global properties for a bunch of FRBs. So Craft survey at ASCAP at the moment has localized 18 FRBs, and galaxies have been identified for 16 of them. So this slide here kind of represent the high resolution view of the sample of FRB host, for which we were able to obtain the observations with the Hubble telescope. So here the blue color shows observations in ultraviolet, and red color is the infrared observations, and black ellipses are sort of second sigma, 2 sigma uncertainty on the position of the burst itself. Yeah, so we see that the majority of FRBs are offsets from their host galaxy centers, and they are mostly a mix of spirals and more lenticular system. So in this latest study by Mannings et al., they also found that FRBs are not really happening in the regions of elevated local star formation in the galaxies compared to the mean global value for these hosts. And we have the complete list of FRB hosts with all the properties in frbhost.org. So please go and check out the properties on this website if you are interested. Yeah, so then now it was time to study the whole population of FRB host population altogether. So combining the new observations with the published data, we accumulated a sample of 16 FRBs with secure host association following the path probability greater than 90%. And we also included the repeating FRB happening in M81 and one of the ASCAP flies-eye FRB 17, 10, 20 due to their low probability of chance associations. So basically our final host sample consisted of host of 6 repeating FRBs and 10 non-repeating FRBs. So the pink here shows all the repeating FRBs in our sample. Yeah, so then using this host sample, we first compare the FRB host population with the underlying galaxy data from the Primus survey of galaxies for the redshift less than 0.5. So basically we are in the same range as that of FRB host galaxies. So I guess it's okay to compare them. So plot on the left here represents the current star formation rate as a function of the stellar mass. So you can see that most of the FRB hosts lie in on or around this cloud of star-forming galaxies, but they are offset from the star-forming main sequence, which is kind of this purple line. So all these sources are offset. And just to compare, I have plotted Milky Way here. So Milky Way is also kind of lying where in the same line of constant specific star formation rate here. Yeah, and we note that 2 of the FRB hosts are kind of in this quiescent cloud of galaxies. So plot on the right here shows the color magnitude diagram, and it kind of gives an overview of the overall stellar population in these galaxies. So the late type galaxies, which have a lot of star formation going on and therefore young stellar population, lives in this blue cloud here. So we call them blue galaxies, while the massive red and dead galaxies, which are characterized by very low star formation and therefore old stellar population, lie in this red zone. So we call them red galaxies. So we see that the FRB hosts kind of appear to lie on the luminous side of this absolute magnitude diagram, mostly near the blue cloud and the green valley region. So the green valley region is the region where galaxies are sort of transitioning from being very star forming to quiescent system. Okay, so this is the same plot, but the difference here is that I have weighted the background Primus data by the stellar mass. So where the first plot shows where the most of the oops, I got my cursor wrong. Yeah, so where this first plot, oh, it's not working. Okay, where this plot shows where the most galaxies are, this plot, sorry about that. Yeah, this shows where most of the stars are in the local universe. So as you can see that majority of the FRB hosts are not tracing the massive red galaxies where most of the stars lie in the local universe. So, and also we see that these hosts do not seem to align with the color magnitude diagram space for the peak of the blue galaxies, which is kind of here. So they are not either aligning with the peak of the blue galaxies or not anywhere near the red galaxy peak here. So this could have a implication that FRB progenitors are not solely determined by delayed channels. By delayed channels, I again mean where the lag between the star formation in the galaxy and the birth of the progenitor itself is more than a giga-year or so. And such channels could be accretion-induced collapse of a white dwarf or merger of compact stars in the binary system. Yes, so to quantify this effect, we examined the null hypotheses that FRBs track the stellar mass. So for doing this, we use the double Schechter model of the galaxy stellar mass function for all the star-forming galaxies, and as well as the passive galaxies together and separately for the galaxies in the redshift range of 0.2 to 0.5. So then we took the weighted computed weighted cumulative version of this function, and then we compared that with the FRB host mass distribution, which are plotted here. So this is for the FRB, and then blue is for all the star-forming galaxies in the sample, red is the quiescent and passive galaxies, and brown is kind of combining both of them. So our KS test shows that FRB hosts do not track the stellar mass of the field galaxies because of really low p-values here. So next, we tested the null hypotheses that FRB hosts track star formation rate. So for that analysis, we use the star formation rate distribution function here, which is derived from GALAX data. So we are really looking at the local universe, which is a redshift of about 0. So this function was derived from the UV and IR luminosity Schechter functions for the local universe, as I said. And then we took the weighted SFR of this function to obtain this SFR volume density distribution function. And then we took a cumulative version of this function and compared with that of FRBs here. So then the black is again the FRB SFR, and this brown line is what you get after doing that analysis for the field galaxies for local universe. And again, it has really low p-values, which tells us that FRB hosts are not either tracking the star formation rates in the local universe. And then we also investigated the specific star formation rate. So specific star formation rate is basically the ratio of star formation rate per unit mass. So yeah, so we compared the SFRs of the FRB host in our sample with that of with that of SFR functions, which are normally modeled either by a log normal or double exponential profiles here. And this is the work from Albert et al. 2017. So these functions, I should mention that, are derived from the star forming sample of galaxy only defined by the main sequence. So they have a really strict cutoff, and they're only selecting the group of galaxies which are on the main sequence. In the Cosmos survey and the GOOD survey, and again, the redshift range is where we have seen most of our FRB host galaxies lying. So we combined all these functions for all the individual mass bins, and then again took weighted it by the specific star formation rate itself. So it's a weighted version, and then took a cumulative sum again. So here is the blue plot, and the two dashed and normal lines are for the different profiles here. And we see that FRBs are far away from where the most of the star forming galaxies of the main sequence are living. So this pretty much matches up with the diagram that I have seen, I've shown you before, that FRBs are offset from the main sequence. So that is kind of a quantitative version of that plot here. So then again, our KS test rejected the null hypothesis here. And thus we conclude that FRB hosts have a lower stellar mass, star formation rate, and specific star formation rate than randomly selected field galaxies, which are weighted either by their stellar mass, star formation rate, or specific star formation rate. So this makes it really tricky to actually understand what's going on here. So FRBs could track some other property that is maybe yet to be identified. Then moving on, we have plotted the BPD diagram, which is the very famous diagram where the nuclear emission line ratios, which are derived from the optical observations, kind of determine the dominant source of ionization in the galaxy. And it's also a very useful way to distinguish between the star-forming galaxies, the Cepheid or AGNs, and liner galaxies. So we observe that FRB hosts are not drawn from a specific class. For example, they are not all star forming or they are not all liner. They kind of mixture of liner and star forming, as we can see here. So those are the dominant emissions for these hosts. And I also note that we had the spectral line information for some of the repeating FRBs and not for all. But for those three bursts, for those three FRBs here, we can see that they're all lying in the star forming region, but again, not on this very solid black line, which is the star forming main sequence. So this kind of, again, agrees with what I have mentioned before. Okay, so next what we did, we performed a differential analysis of the host population of the repeating and non-repeating FRBs. So here we are comparing their stellar masses, their star formation rate, the stellar mass, the projected offset. So projected offset is the physical distance between where FRB is happening in the galaxy as compared to the galaxy center. And then we also compare the metallicities, their R1 magnitudes, and their specific star formation rate. And we found no significant differences in the global properties of the host for these two populations in the analysis. So all p-values are greater than our significance value of 0.05. We then went on comparing the global properties of FRB host with that of other transients, which includes ULX, which stands for ultra-luminous X-ray sources, long GRBs, short GRBs, core collapse supernovae, superluminous supernovae, type 1a supernovae, which are sort of proxies for accretion-induced collapse of white dwarfs. So we followed the method of Boschneck et al. To correct for redshift evolution by scaling the stellar masses and star formation rate of each of these host galaxies, plus the FRBs to be statistically representative of Z equals 0 galaxies. And here are the results. So here again are the same properties, projected offset and star formation rate and everything. And then the different colors are the distributions for different transients. Here, red is non-repeating FRBs and blue is repeating FRBs and black is all FRBs combined here. So we found the FRB host to be statistically indistinguishable from core collapse supernova and short GRBs here, just looking at their p-values. And we also found that the ULXs and the type 1a supernova projected offset are similar to FRB hosts, but their host masses and star formation rate are statistically different from FRB hosts. They're on the higher side. I will also point that there is a small bias in this ULX sample because this is bias against the low mass galaxies because these are derived from the Hirkat survey. But even though if you just look at the ULXs in the local universe, like less than 40 megaparsec or so, you still see that the host galaxies, like on the masses as well as the star formation rate, is on the higher side. While from the host galaxy considerations, we could statistically say that LGRBs and superluminous supernovas are less likely for FRBs, for all the FRBs combined together. But when we compared the repeating and non-repeating populations separately, we did find some similarities between the repeating FRB host population and the hosts of these transients. So this may be because here the sample size is really, really small for repeating burst. And then the host of R1 can have a very larger effect, like it's pulling in a different direction, and that is affecting the overall repeating host population. So yeah, further investigations are really needed to be able to say whether this effect is real or not. Again, a few things I would like to point here that one is likely to find an extreme p-values with the more KS tests you do, and we haven't corrected for that. And also there is a big caveat here that all of these transients that we are using, they assume a dominant channel, which may or may not be true for FRBs. So this is still very early days for these sorts of analysis, and I won't make any robust conclusions here at that moment, but just say that the FRB host are pretty much similar to that of core collapse supernovae and SGRBs. So moving forward, we also conducted the radio follow-up for our all-craft FRB host galaxies with either the compact array or the VLA to search for radio emissions from these host galaxies. And for all the hosts, we did not find any compact persistent radio source similar to what has been associated for FRB 121102, and now also for one of the twins of FRB 121102 from the FAST survey. So, but however, we did detect radio emission from some of the hosts, which we attribute due to the star formation in the galaxy itself. Okay, so moving on, following the recent works of CHIME et al., we compared the host normalized offset distributions of the largest sample of FRBs in their host with that of the galactic sources. So initially, CHIME et al. Used the Milky Way disk scale length to be 4 kiloparsec, which is the upper end of what they find for literature, in the literature. And then they used this particular scale length to compute the galactocentric offsets for these sources. And this is also what I have presented in FRB 2021. So just looking at that and comparing their offset distributions with that of FRBs, we can see here that we couldn't reject the null hypotheses that these are drawn from the same underlying distribution. But recently the author got in touch and mentioned that they have revised the value of this Milky Way disk scale length, which is now the median of the previous estimates, which is now 2.6 kiloparsec. And they changed this as per the reviewer comments, and this change has also affected our previous results. So now using the updated value of offsets and then comparing for these particular sources with that of FRBs, we can see that the galactic neutron star population is not consistent except for the low mass X-ray binaries. So this actually shows that even a small parameter like the Milky Way scale length can change these results. So we should really look at what are the assumptions and what are the caveats going on, and we can't really make any strong conclusions just by looking at this plot, because there are so many assumptions going on with the data. So something to be careful of.
Shivani.
Yes.
That's super interesting. Did the author, I mean, so in your calculations there, did you strictly use the median value, or was there an estimate of some sort of credible or confidence interval or uncertainty to act, like, was there an accounting of uncertainty, I suppose, in the disk scale length to that went into the calculation that it's mostly not consistent?
Yeah, so that's a good question. And I think I have to go back and look at the latest CHIME paper, because I'm not sure if this updated scale length result is still on archive, because they are still working on the comments from the reviewer. But yeah, I'm interested to see exactly that. And that number will be helpful just to look at the confidence level of what could be the Milky Way disk scale length error and how that could affect our data. But yeah, I don't have that number at the moment. Sorry. Yeah.
Vicky, you have your hand up.
Yeah. So the Milky Way radio pulsar population is quite biased by the properties of the surveys that found them. And so I'm wondering, did they compare with the observed population of radio pulsars or with some model for that population?
I think this is the observed population, because the data that I found in their GitHub repository had different sources, and then it had like the RA index for that particular sources, which they use to define the offsets. So I think this is not a model, and this is like the actual data. But yes, I agree, there are so many biases going on here. Like for example, if you look at the FRBs, they're not really towards the host centers, which could be maybe there is too much, too many free electrons, and we couldn't really detect FRBs which are near the host centers, or it could be a real effect. So yeah, I agree that there are many biases in action at this moment, but I think that this is not a model, this is the real data.
Right, so there could be, I'm less sure about the LMXPs and HMXPs. For magnetars, it's not, it's a little bit better. The selection biases are not as severe, but for pulsars, it's pretty severe.
Right. Yeah. Okay. Yeah, I agree. Okay, so our last analysis was motivated by the discovery of an FRB in the globular cluster in M81 system. We then compare the host normalized distribution of burst with that of globular clusters in the late and early type galaxies. So we use the published globular cluster data associated with spirals such as M81 and Andromeda galaxy, and some of the ellipticals such as NGC 821 and 4278. And we note that the M81 data is mostly dominated by the disk population of globular clusters, where majority of the clusters are within the 10 kpc from the galaxy centers, while for other we do see a mix of both disk and halo population. And even for most of them, like for the elliptical ones, they all the GCs can be found up to 100 kpc from the host galaxy center. So then we went on again comparing the same offset distribution of FRBs with the GCs, and we found that the offset distribution is mostly statistically not consistent with that of globular clusters. So yeah, most of these values are less than 0.05, but then again, this is on the edge, and we need more FRBs to be able to say something robust about it. But we did see that for M81, it's greater than the significance level, which could be because this is mostly dominated by the disk population rather than disk and halo population. So yeah, as I said, there are some caveats here. We know that the globular cluster frequency scales with the stellar masses, and the FRB host population at the moment spans like 4 orders of magnitude in stellar mass. And also in the current FRB host sample, we did not see any elliptical galaxies. So yeah, I would reiterate that a much larger sample of precisely localized nearby FRBs are really required to pursue this further.
Mohit, you have your hand up?
Oh, yeah, Shivani, can you go back to your previous slide?
Yeah.
Yeah, I was surprised how, I don't know if there are 340 high quality GC candidates. For example, Nantiaz and Hashra, they did spectroscopic follow-up of 74. So that is true. Like I think in this paper they do say that 74 are spectroscopically confirmed, but in this paper they say that there are 340 high quality GC candidates. So this is still GC candidates 340, but out of those only 74 are spectroscopically confirmed. So yes, you are correct. Oh, okay. Because fine, I had this number of 120 something they found after removing stars, but maybe I'm wrong. Okay, that's cool. And you and you are saying that all 34 these candidates are disk-like?
Yeah, so basically they are all within the 10 kpc of the host offset. Like, so mostly those, so if you look at in the plot here for M81, yeah, so they are mostly located within 10 kpc, or there is few, so I have said 30 kpc. But if you compare this with this, the scale is pretty much big. So here you see the disk population kind of lying on the top of the galaxies here, and then you can clearly see the halo population. But for this particular, even for the Andromeda, you can see that there are some of the globular clusters in the disk, around the disk, and then there is a halo population here. But for M81, because this is very faint, like it's very difficult to detect the globular clusters, and since the discovery, I know there are groups who are submitting proposals, HST proposals, to specifically study the halo population of M81, because that particular FRB came from the globular cluster, which is about 20 kpc. So that is again mostly, so that is even not even very confident whether that's a halo population or a disk population. But I think looking at the colors and all the properties of the globular cluster, it's mostly towards the halo. So yeah, we are missing some of the data for M81 in this case, and there are campaigns that are currently ongoing to just study that halo population. But with disk population, I mean that they're all within 10 kiloparsec from the galaxy center.
That's right. I think so. The thing is, the current sample is anyway biased against detecting halo population.
Yeah.
And also, like another point is actually, as for some reason, I'm sort of reading more about NGC 4278.
Okay.
And again, I'm surprised 1,830
Yes.
GC candidates. Are they all
So again, when I say candidates, these are good candidates. They are not confirmed, but I think this is a very good galaxy that Duncan Forbes groups are studying as a part of SLUG's survey. So they might have some spectroscopic observations, confirmation for this particular galaxy here. So maybe that is something to check out if you really want to just see the GCs which are spectroscopically confirmed. But yeah, these are all good candidates according to these papers.
I'm asking because I read from this paper that they have 85 candidates. So I thought that maybe they're selecting out of these whole bunch.
Yeah, have a look at these papers, and I'm happy to share the data with you if you want to play with these GC candidates.
That would be great. Thank you very much.
Thanks. Yeah, so let's talk about future a bit. So we are working towards upgrading the current craft system. With we, I really mean like Keith and the engineers. So the current craft system does the incoherent sum searches for FRBs, and this coherent upgrade, or CRACO, will enable a full coherent search via fast imaging of visibilities. So this will make ASCAP 5 times more sensitive in the detection of FRBs than the current method. And thus, in the coming future, ASCAP will be delivering 1 FRB or so per day with arcsecond localizations. I'm very excited to announce here that we have been awarded 180 hours of BLT time to observe 50 ASCAP localized host galaxies in the coming years, in the coming 2 or 3 years. So yeah, watch out the space for more host galaxy observations and analysis. So I will finally conclude now. So we have seen that FRB host population is showing a dearth of red galaxies, meaning FRBs are not usually found in massive old red and dead galaxies. So the next, what we are doing is we are analyzing the age of the stellar population for these FRB hosts using the prospector stellar population age modeling, and that's something which is in progress. And so we see that the FRB hosts here are moderately star-forming galaxies with masses offset from the star-forming main sequence. We also see that FRB hosts do not track stellar masses. star formation rate and specific star formation rate of the field galaxies. In our analysis of compared, so is there a question? Okay, I'll go on. So we also find that there are no significant differences between the hosts of repeating and non-repeating FRBs. We find that the host population at the moment is looking statistically consistent with hosts of both core collapse supernova and SGRBs. And that finally, the host normalized FRB offset distribution is statistically distinct from the offset distribution of galactic sources in globular cluster in the late and early type galaxies. And just my final slide so that we can have some nice discussion about it. So I think this is how the picture looks like according to Bing Zhang. So following the detection of the galactic FRB now, the prevailing view at present associates FRB with magnetars whose extremely high magnetic fields provide a reservoir of energy that can produce FRBs. So I really like this block diagram. It shows the most conservative scenario for FRBs, which is sort of invoking a magnetar model to account for all FRBs in the universe. So here the blue boxes are the observational facts and the gray boxes refer to the speculations. So yeah, instead of having the population as repeaters and non-repeaters, what Bing has done, they have considered a possibility of active repeaters versus regular repeaters. And I find that very interesting. So according to this diagram, the active repeating FRBs might come from special magnetars that can be created by short GRBs, long GRBs, and superluminous supernovae channels. And here, these pictures just represent the stellar population of their host galaxies. So like for the long GRBs and superluminous supernovae, there are young stars. And then for the NS-NS merger, the stellar population is old. So yeah, and then the remnants of such scenarios are these special magnetars, which are young sources, let's say possibly age less than 1,000 years or so. And then on the other hand, you have this regular magnetars, which can be made from, so this is something I have added, extending on the idea of Big Bang. So then these regular magnetars can be formed from channels such as core collapse supernovae and maybe from accretion-induced collapse of Wydorf. So I'm not sure about what type of magnetars these models can make, especially AIC of WD and this NS-NS merger. I guess we really need to find one to know that. So the magnetar remnant for this particular scenario are slightly older than this scenario. So their ages are more than 1,000 years or so. And here again, from the PPT dot diagram, we see where magnetars are living. And we can see that the magnetars might live up to, let's say, 100,000 years, and then their magnetic field sort of decay and lose the status. Was there any question, Vicky?
You probably said it, I missed it, but for the coherent craft survey, what is the timeline for that?
So that is a good question. That is to be TBC at this moment, but I think Keith is working really hard on that, and we might expect first slide sometime end of this year.
Thank you.
Okay, yeah, so I think my conclusion is that it may be possible that the FRB progenitors themselves could be formed by various channels, and there is no dominant channel, which sort of agree with what we are looking with the host population analysis, where the FRB hosts are consistent with those of both core collapse supernovae and SGRBs. And also the fact that we do not find the host sample to be dominated by an exotic subpopulation of either really old stars or really young stars, which are explicitly found in red-ended galaxies and star-forming main sequence galaxies. So they are drawn from, instead, they are drawn from a very general stellar population. Yeah, and I will stress on the fact that the key really is the precise localization and high resolution environment investigations of nearby FRBs to address the question of FRB projection. yes, now I'll stop talking. Thanks.
Thanks, Shivani. That's really interesting stuff. Okay, so now we can open the floor to questions. I see that Emmanuel just raised his hand. Go ahead.
Yeah, many thanks, Shivani. It was a great talk. And forgive me, I was not at FRB 2021, but still it was great. So I think at least in the context of, I guess, Bing's conservative picture, does the last point on your initial sort of conclusion slide regarding the question I asked about how, there's tentative evidence for a difference, a statistical difference between how these things are distributed within their host galaxies. Does that not say something interesting about, I guess I'm wondering if Bing's picture still holds in the face of evidence like that?
Yeah, I think so. It does hold because with this picture, you can't, okay, so you have a FRB progenitor that can be made by different scenarios. So that is sort of what we are seeing, because we are not seeing any special host population which only has old stars, and we can confidently say that it's delayed channels only. But we are seeing kind of mixture where the host population is also consistent with core collapse supernovae, which is believed to have young stars and star formation is going on. But then on the other side, we also see the host to be consistent with short GRBs, which are on average mostly older stellar population. So I think at this point, the host galaxy analysis is not a smoking gun. Like, it's very mixed. So I think in this scenario, the local environment plays a very crucial role, because, for example, the M81, if you look at the M81 case, it's a very star-forming galaxy. So you would expect, okay, maybe FRBs are produced by a core collapse supernova, but then you go and see the FRBs coming from the globular cluster, where the stellar population is old. So that kind of makes things very tricky to understand what's going on just looking at the host galaxy demographics.
Thank you.
Okay, other questions? Oh, Mohit just raised his hand. Go ahead, Mohit.
Shivani, a very nice talk. Thanks so much. So my question is related to what Emmanuel asked. So active repeaters, the first thing is, do you consider R3 as an active FRB?
Sorry, I'm not yet familiar with R1 and R3, so you have to say the full FRB name.
Means the FRB that is localized to a spiral galaxy at a distance of 149 megaparsec.
Okay.
The periodic FRB, I'm sorry.
Right. Okay.
Just periodic.
Yeah. So that is interesting, because
Now,
I think that, oh, sorry. Okay, yeah, go ahead.
No, please.
No, I didn't catch your full question. I just interrupted you. So please ask your question.
No, I think my first part of the question is, like, if you consider, do you consider R3 as an active FRB? And why I'm asking this is, if R3 is an active FRB, then I actually don't see any of these three categories can actually explain the R3 progenitor well. Because we know that galaxy is massive and have high metallicity, that it cannot be, cannot have a long GRB or superluminous supernova progenitor.
So yeah, so just looking at where the FRB is in the galaxy, we see that it's offset from the very star-forming region. So that kind of rules out this, as what they have said in the paper, that magnetars are less likely to have those sorts of age when there is a drift between, when they are drifting towards away from the star-forming regions. So I think that's why they say in the paper that it's mostly consistent with high mass X-ray binaries ages than that of magnetars. So in that scenario, like, this is only the conservative picture for magnetar engines. But if the progenitor turns out to be high mass X-ray binaries, then maybe something else is happening.
Okay, other questions? Vicky, you have your hand up. Is that a new question or?
No, I think I just forgot to put it down.
Okay. Okay, do we have other questions for Shivani? Okay, if not, then I think we can end the journal club. We're right on time, so that's nice. A really interesting talk, Shivani. It's really cool stuff that you guys are doing. So congratulations on some really excellent work. And I will go ahead and end the recording.